crystals and broken rocks, almost nothing in the natural universe has many sharp edges.
Although many objects have strange shapes, the list of round things is nearly endless. From simple soap bubbles to the entire observable universe. Spheres tend to form under the influence of fundamental physical laws. This tendency is so common that we often default to imagining things as spheres for easier reasoning.
Even when knowing that the object is not actually round.
To understand why an object in that case is a sphere, then you haven. Spheres in nature form due to forces like surface tension that tend to shrink objects in all directions.
With liquids forming soap bubbles, surface tension compresses air evenly in all directions.
At the moment of formation, it encloses a certain volume with the smallest possible surface area. This creates a maximally taut bubble, as the soap film cannot be thinner than the absolute minimum. Through simple calculus, it can be proven that a sphere is the only shape with the smallest surface area to contain a closed volume. In fact, we could save billions of dollars annually on packaging materials.
If every shipping container and food packaging in supermarkets were spherical.
On Earth, one way to make beads is to drop molten metal droplets of predetermined mass from a height down a long shaft. The metal droplets gradually solidify until they become spherical, but need enough time to harden before hitting the bottom. On orbital space stations, where everything is in a weightless state, you only need to gently spray molten metal droplets of precise mass to create perfectly round particles. They float while cooling, then solidify into perfect spheres.
For large cosmic objects, it is energy and gravity combined that shape them into spheres. Gravity is the force pulling matter from all directions toward the center.
But gravity does not always win.
The chemical bonds inside solid objects are very. The Himalayas rise against Earth's gravity due to the elasticity of the rocky crust. But before getting excited about Earth's majestic mountains, you should know that the elevation difference from the deepest ocean trench to the highest mountain peak is only about 20 kilometers. Meanwhile, Earth's diameter is nearly 13,000 kilometers. So, contrary to the image of tiny humans standing on Earth's surface,
Earth on a cosmic scale is actually quite smooth. If you had a giant finger and ran it over Earth's surface, it would feel as smooth as a billiard ball. Classic globe models depicting mountains with raised, bumpy land portions
have essentially exaggerated reality.
This is why, despite having mountains and valleys on Earth, including the relative flatness from pole to pole,
when viewed from space, Earth still appears as a perfect sphere.
Earth's mountains are still quite small compared to other mountains in the solar system. The largest mountain on Mars, Olympus Mons, is 20 kilometers high and nearly 480 kilometers wide at its base,
making Mount Everest look like just a hill. The universe's mountain-making formula is very simple.
The weaker the surface gravity, the higher mountains can rise.
Mount Everest is the highest limit that mountains on Earth can reach. Before the elasticity of the underlying rock layers can no longer bear the mountain's weight. If a solid object has sufficiently low surface,
the chemical bonds in its rock will resist its own weight. When this happens, almost any shape can exist.
The two most famous non-spherical celestial bodies are Phobos and Deimos,
the two potato-shaped moons of Mars.
On the 20 kilometers wide celestial body Phobos, a person weighing 68 kilograms would weigh only 0.1 kilogram. In space, surface tension always turns a liquid droplet into a sphere. Yet this droplet has a very large mass, regardless of what material it is made of.
Gravity will still cause it to be spherical. Whenever you see a small solid object that is suspiciously perfectly spherical, you can conclude that it formed in a molten state.
Heavy and large gas clouds in the galaxy
can coalesce to form fairly round gas spheres called stars. But if a star orbits too close to an object
with significant gravity,
the sphere can be distorted as its matter is pulled away.
Too close here
means close to that object's Roche limit. named after the 19th century mathematician Edward Roche,
who studied in detail the gravitational field between a pair of stars. The Roche limit is a theoretical boundary surface, bulging like an onion at both ends to form a dumbbell shape,
surrounding two orbiting objects. If gas from one object crosses its own boundary, it will fall toward the other object.
This phenomenon is commonly seen in
when a star swells into a red giant and exceeds its Roche limit.
That giant star is distorted into a different shape,
no longer a sphere but more like a teardrop-shaped chocolate candy.
Moreover, if one of the two stars is a black hole, its position will be revealed by continuously sucking matter from its companion star. The swirling gas,
after escaping from the giant star that exceeded its Roche limit,
is heated to extremely high temperature and glows brightly before falling into the black hole and disappearing from view.
The stars in the Milky Way form a huge flat circle.
With a diameter to thickness ratio of 1000 to 1, our galaxy is thinner than the thinnest piece of paper in the world. It is not spherical,
but it may have started out that way.
We can understand this thinness by
assuming that the galaxy was once a giant gas sphere, contracting under gravity,
slowly rotating around an axis. During the contraction, the sphere spins faster and faster.
The galaxy flattens due to increasing centrifugal force, which tends to pull its parts outward.
Any stars formed inside the galactic cloud before contraction will maintain wide and fast orbits. The remaining gas easily collides with each other,
like a collision in space between two molten marshmallows,
and is compressed into the central plane, where all later generations of stars, including the Sun, are born. The current Milky Way, neither contracting nor expanding, is a mature gravitational system, and one can observe stars rotating above and below the disk as remnants of the original spherical gas cloud. This common flattening effect of rotating objects is the reason why the Earth's diameter from pole to pole is smaller than the diameter at the equator. Not by much, only about 0.3%, roughly 42 kilometers. But Earth is small, mostly solid, and does not rotate too quickly. Every 24 hours, Earth causes objects at the equator to move at a speed of 1,600 kilometers. Consider Saturn, a gas giant that rotates very rapidly, completing a day in just 10 hours and 30 minutes. Its equator rotates at about 35,500 kilometers per hour, and its pole-to-pole size is noticeably 10% smaller than its equatorial diameter. This difference can even be recognized by amateur telescopes. Flattened spheres are often called oblate spheroids,
while spheres stretched from pole to pole
are called prolate spheroids. In everyday life,
hamburgers and hot dogs are great examples of these shapes.
We use the effect of centrifugal force on matter to better understand the rotation speeds of extreme cosmic objects. Consider the case of a neutron star. There are stars that rotate on their axis at thousands of revolutions per second.
We know they cannot be made of ordinary matter,
because if they were, they would spin so fast they would tear themselves apart. In fact, if a neutron star rotates faster than 4,500 revolutions per second, its surface would move faster than the speed of light.
This indicates that
this material is unlike anything else. To visualize a neutron star, imagine compressing the entire mass of a sun into a ball the size of Manhattan, or stuffing about 100 million elephants into a lipstick tube. To achieve this density, you must compress all the empty space and atoms around the nucleus, and between the orbiting electrons.
This would squeeze nearly all electrons into protons,
creating an electrically neutral neutron ball, with an extremely strong surface gravity. Under such conditions, a mountain on a neutron star, only as high as the thickness of a sheet of paper,
would still require more energy than an Earth climber conquering a 5,000-meter cliff.
In short,
where gravity is strong,
high points tend to collapse, filling in the low area.
For all these reasons, we believe
neutron stars are the most perfect spheres in the intense galaxy cluster. Their average shape can provide us with deep insights into astrophysics. Some have rugged surfaces, some are stretched into thin filaments. Some form vast, fragile flat. No cluster has a gravitationally stable shape, i.e., spherical. Some clusters are stretched to such an extent that the universe is 14% insufficient for their constituent galaxies to travel from one side of the
We conclude that clusters formed this way
because the gravitational interactions
did not have enough time to shape a cluster.
But other systems, such as the Coma Galaxy Cluster, have a beautiful spherical form,
telling us immediately that
gravity has molded the entire cluster into a sphere.
And as a result, you can see a galaxy moving in one direction or another.
It's so, the galaxy cluster cannot be rotating too rapidly.
Otherwise we would observe a disruption, like what once happened to the Milky Way.
The Coma Cluster, similar to the Milky Way, is also gravitationally
relaxed.
This concept has many implications, including the average velocity of galaxies in a
can serve as an excellent indicator of the system's total mass.
Regardless of whether the objects used to calculate the average velocity contribute to that
relaxed.
For exploring dark matter that does not emit light,
without which, perhaps to this day, we would not have detected the ubiquitous presence of dark matter.
The sphere encompasses all spheres,
the largest and
most perfect being the entire observable universe. From every direction we look, galaxies are receding
at speeds proportional to their distance from us.
This is the famous signature of an expanding universe,
discovered by Edwin Hubble in 1929.
When you combine Einstein's theory of relativity with the speed of light, with an expanding universe, and the dilution of mass and energy in space, as a consequence of expansion, then from our position looking in all directions, there will be a distance, where the recession velocity of a galaxy equals the speed of light. Beyond this distance, light from any luminous object will lose all its energy
before reaching us.
The universe outside this spherical boundary thus becomes invisible, and as far as we understand, that part of the universe is unobservable. There is a very common variant of the multiverse idea, which suggests that the universes constituting the multiverse are not completely. They are distinct spatial pockets, not interacting with each other, existing within a continuous space-time structure, like boats on a vast ocean, far enough apart that their time circles do not intersect.
As far as each ship can determine,
without additional supporting data, it would only see itself as the sole ship on the ocean. The spherical model is truly a rich theoretic,
helping us explain many issues in astrophysics.
But we should not be too rigid with the sphere, as somewhere in a corner of the universe, more wondrous shapes may exist.